electron volts. So what we have there is supernova neutrinos, the diffuse supernova background, then of course reactor neutrinos below 10 MeV, also solar neutrinos. So these are the neutrinos that are interesting for coherent interaction. And of course, also the neutrinos that come out of the spallation source. I will be talking about this a bit more in detail, how these neutrinos are created. So these are the sources that will result in the 7's interaction. And why bother with 7's? Yeah, so these are the sources. And what I want to show you here is what need to be done to detect 7's. I already mentioned that this for coherent interaction, the cross-section scales with the neutron number squared, and which makes it large. So that this is the 7's cross-section in comparison to the beta decay. And consequently, this means you don't need a large detector. You can have a small detector setup. So this, for example, is the coherent iodine detector where the first detection of 7 occurred in comparison to, for example, xeno, which you need to get a lot of inverse beta decay events. However, what we want to detect in the end is this very tiny recoil of the nucleus that has been hit by the neutrino. And the maximum recoil energy scales with the mass of the nucleus. And you can see here in this figure for energies below 50 mega electron volts, this recoil energy at spallation sources results in a maximum value of a few tens of keV, and at the reactor side, it's even just a few keVs, which means that you need a detector with a much lower energy threshold than that. What makes it so tough to detect such small. You need a technology that is capable to get to this low energies. So why bother? There are a lot of interesting physics cases for 7. First of all, thinking about the process, supernova explosion, then in the stellar collapse, more than 99% of the energy is emitted in the form of neutrinos, and they have the right energy, as you can see down here, to be scattered coherently in the output, which means that to be able to model supernova explosions, you need to know this cross-section very well, which means it's important to have information that holds there. But also, it's a nice interaction to detect a potential supernova explosion on Earth. Then there are also other detectors that are capable to see 7's, and these are all the dark matter detectors. The dark matter detectors, they are looking for the recoil of dark matter particles, which is the same signature than for the neutrinos, which means the more sensitive they get, as you can see here, the more they will get to the reach of the environmental neutrinos, the so-called neutrino floor, neutrino fog. And for example, so here are the bound 8 neutrinos of the sun. And very recently, in the last few weeks, actually, a first very strong hint of the neutrinos that's been reported by Xenon and Ton and Panda X. Both of them got almost 3 sigma from their detection of bound 8 neutrinos. So meanwhile, we reached this neutrino floor, which makes it very interesting to have an independent 7's detection to be able to actually confirm that from the cross-section, and to make sure that it's possible to know if a recoil is detected there, how much you have to assign to neutrinos and how much to a potential dark matter candidate. So what else you can do? There's the Weinberg angle in the cross-section. I've mentioned that this term is almost 0. However, it's not exactly 0, which means if you have a lot of 7's events, can determine the Weinberg angle. And this is interesting because these very precise detections only happen up to not higher energies of colliders. And with 7's, you can actually determine this value here at low energies, which is also a nice test of the standard model. The same holds for the nuclear neutron form factor that goes into the cross-section. Here, the different experimental approaches are actually interesting because they are complementary. spallation sources, this form factor, as you will see later, is not exactly 1, so you can measure the shape of the nucleus. And for the reactor side, this value is very close to 1, so there you get the normalization. So having both in the end will be a way to directly access the neutron form factor, which is also very interesting. Then we have all this beyond the standard model physics cases, which includes neutrino interactions. In non-standard neutrino interactions, what you do there is you just assume you don't know what happens during the scatter event. And this is described by a 4-point interaction, it's epsilon parameters. And then you use your detection to set limits on this epsilon parameters, which works very well. That you can here for Coherent, and turns out that you can also set very, very tight limits here already, also in comparison to big collider experiments. And last but not least, regarding the detection at reactor side, at some point it might also be an interesting approach for nuclear safeguarding. Here again, the comparison to inverse beta decay, which has a threshold of 1.8 MeV, which is not true for CEvNS. So CEvNS does not have an energy threshold, which means with future generations of detectors, if you are able to access these very low energies, that will be a very interesting way to detect reactor. So in the remainder of my talk, I want to show you how Coherent managed to detect these neutrinos. And this is the Coherent collaboration here. Coherent is located at the spallation neutron source in Oak Ridge, Tennessee, in the US. The spallation neutron source is a time decay fast source, and the neutrinos are created from pion decay. So how this works is that there's a proton beam that hits this mercury target. Pions are created, and more than 99% of these pions decay at rest. The pi plus results in muons and neutrinos. So we have this prompt neutrino component that is created within 1 microsecond after protons target. And then the muons, of course, decay, which means that we get more neutrino flavors out of there. And overall, as you can see down here, it's expected that all of the neutrinos basically arrive after 8 microseconds from after the proton interaction. The spallation neutron source is a pulse beam, 60 Hertz, which is very helpful for the background suppression because we know exactly when the neutrinos arrive. And the neutrinos have the correct energy below 53 mega electron volts, which means we get an interaction. And thanks to the high power of 1.7 mega electron volts, we expect about 10 to the power 20 photons on target per day, which means that we get 0.3 neutrinos per QT. And this results in a lot of neutrinos in Neutrino Alley, which is where all of the Coherent experiments are located. Neutrino Alley is in the basement of the SNS, in a distance of about 20 to 30 meters from the target. And it turns out that this is a great location to detect neutrinos because there's a lot of material, a lot of gravel between the experiments and the neutron source, which is helpful because it's the neutron source that creates neutrons that are background to a CEvNS detection. And in the neutrino alley, this background is very low. And depending on the location, almost negligible in the end. Coherent has a multitude of CEvNS detectors. And the goal there is to actually measure the n-square dependence cross-section. Up to now, there have been already several successful detections. The first one is iodide. What you can see here in the figure is the dependence of the cross-section on the Newton number. And for the system iodide, for the full data set, in the end, the null hypothesis, no CEvNS was rejected by 11.6 sigma. Then there was the second detection, argon. Here, for this first data set, rejection of the null hypothesis of 3.5 sigma has been achieved. So we have 1 point here, 1 point here, And what I'm going to talk about today is the point here in the middle, for germanium. I'm going to show you the experiment that resulted in us being able to put the point there and discuss this analysis. So the setup here is called Janina, and it's located at the exact location where the cesium iodide detector has been placed in 19.2 meters target. The experiment consists of eight high-purity germanium spectrometers. I think I already highlighted a lot that we need this energy threshold. To get this, we have the reverse coax design, which means that we have a point contact down here. The point contact ensures that we have this very good energy resolution of 110 electron volts, because it makes sure that we have a capacity. And then the other interesting feature about this design is the core here that has been removed. This is necessary to be able to heat the germanium, because in the end, to be able to get the detection with germanium, you need to put high voltage on the crystal, which creates an electric field. And for these large crystals, in this case 2.4 kilograms, that's only possible by removing a bit of germanium to be able to fully deplete the crystal, which means to get an electric field over the full volume of it. And here I wanted to show a bit history on the development of germanium spectrometer, just to give a feeling on why these detectors are so great and what this actually means. The figure up here is also a large germanium crystal, but it has a different design. That is a coaxial detector. And for most figures here, data was collected as a magnesium source. Here you can see X-rays that come out of the source around 100 keV. This data, so this detector is from 2006. And you can see that it's possible to resolve these two peaks. However, now using the inverse coax design, you're actually able to resolve tiny X-rays between, which shows how much this energy resolution has been improved, while the crystal mass is pretty similar. So what do we now expect to see in our detector? So for the energy spectrum, this is what comes out the neutrinos that come out of CEvNS, the mega electron volt energies. And now we need to take into account another effect that is important for germanium, the so-called quenching. Quenching in general means that the energy that is deposited in the detector is not only deposited in one type of energy, but different ones. For germanium, this is ionization energy components. However, germanium spectrometers are only sensitive to ionization energy, which means that for recoil, you only see part of the energy, and this is a very important parameter to know well. Now, to give an idea, for 30 mega electron volts neutrino, we expect a maximum recoil of 25 keV, and with this quenching factor, this only results in an ionization energy of 6.3 keV, following the Linter theory. It turns out that there's a lot of data that confirms this Linter theory, and there are these discrepancies at low energy. However, there's no real GE foundation for that. For the analysis that I'm talking about here, we actually set the energy threshold at a value where all of these discrepancies don't matter. We can just apply the Linter theory, and we don't have a systematic uncertainty. Then, so we need to apply the quenching to expect. And then we also need to form factor, so the shape of the nucleus, due to this neutrino energies being a few tens of MeV. This is not exactly one anymore, but overall, it turns out that we have a 32% reduction of the rate that we expect. And putting all of this together, this is how the spectrum looks like that we want to measure. This maximum energy of 20 keV. So this is the other end for the region of interest for our analysis. And here I want to take a moment to compare reactor experiments, because I think it's interesting to understand a bit better what's different, which makes this detection of reactor site more challenging, and why the CEvNS is such a great place to detect CEvNS. So for the CEvNS spectrum, what you can see here, that starts at 3 mega electron volts, while at reactor down here, the neutrinos have energies below about 12 mega electron volts. And this, of course, means that the recoil energies are much lower. So here's an expectation for germanium. And you can clearly see that at reactor side, the spectrum starts at much lower energies. So I put here the analysis thresholds for the analysis here for Coherent, and then also for CONUS, which is a reactor experiment. You can see that this region don't even overlap for the upper end of this region of interest there. So you can imagine that you need a detector with a much lower energy to be able to see CEvNS at the reactor side. However, once you have this, for similar distances to the source, the commercial power plant at least, you expect much more neutrinos down here. So that's, I think, still very interesting to try to detect CEvNS at the reactor side, because this can really result in a position test of the sample model. Then I already mentioned the complementarity regarding the form factor, which is close to 1 at the reactor side. And then last but not least, there's the background suppression. In both cases, of course, spallation source reactors located over ground, so you need fields. However, the spallation source, thanks to beam correlation, we get an additional factor of the order of 10 to the power 4 of background suppression. And you can imagine that this immediately helps a lot to get the signal out of the data. While at the reactor side, you have to work a lot more, try to get a better shielding to be to get the chance to see anything. So, yeah, so this is the comparison between the two sources, and to be able to use this suppression factor thanks to the beam, of course, you need detectors that are not terribly slow, because if it takes a long time to read out the signal, then you can reduce this correlation. PMTs are very fast. For germanium, there was a bit of concern that it takes a while for the charges to drift. Here you can see half of the diode and the electric field, and it's getting higher and higher towards the readout here. But if you have the action up here, it will take a while for the charges to drift here. So one important task for our analysis was to figure out how long the spectrum takes. How this looks like in the data is waveform here, and you can imagine like this is the point where the charges are created, and then it takes a while for them to drift. And, this point here in the middle of the rise of the charge collection is where the charges then arrive at the readout. So this distance is what we want to know. And you might be wondering actually how I'm able to set this line here. And this is thanks to our drift time measurements. So what we did is we used a coincidence between the germanium and VGO. VGO is spread out as a PMT, so it's basically immediate. And then we put a source between detectors. So we have this starting point when we see an interaction of VGO. And then for the germanium, at some point, of course, there's a rise in the waveform, and we determine the distance in time between the signal. And what we get out, you can see over here. Drift time distribution depends on where the interaction happens in the crystal, how long it takes for the charges to arrive. And it turns out that this is always well within a few microseconds. which is good news, because it means that we can successfully apply this correlation, successfully apply this drift time to our signal expectation. And doing so, on the left is the spectrum what comes out of CEvNS, and on the right is what we expect to detect. And it turns out that all of the neutrinos arrive within 12 microseconds. To mention a detail, so what you've seen on the previous slide is the result of the measurement. And now for the neutrinos, we can expect that neutrinos detect all over the crystal, while our measurement is only so the source has a certain limitation towards the crystal, so there's a bit of bias, which means for this convolution here, what we used is a mixture between simulation and measurement. So the simulation it tells us about the shape of the distribution for a homogeneous interaction inside the crystal. So it's tiny different than what you see here. While we need the measurement to also take into account how much time delay the electron response adds. And all of this combined then leads to this figure here, 12 microsecond arrival time, which results in the suppression of the background of a factor of 7 times 10 to the minus 4, which is still a very helpful suppression of the background that we saw. That's how Gemini looks like. I talked about the detectors already. We have 8 of them, and they are, so that's the copper crystals. They are connected by the cooling finger with the pure down here, which needs to refer this liquid nitrogen to cool them down. And they are enclosed inside a shield. The shield consists of lead, which is green layer here, because of course there's radiation around the environment. And then, as we are close to surface, we also get a lot of neutrons inside this lead. So we need a lot of rain around here to moderate them as much as possible. And this layer of polyethylene is also helpful to potentially remove any beam-related neutrons. And then, last but not least, we also have this which is the very outer layer here. Our muon meter is plastics insulator plates, and they are red out PMTs that are up here. Some impressions from the construction you can see here from our commissioning phase, how everything is set up. You get an idea that there's not too much space in the alley to build anything. Down here, yeah, it's a bit hard to read with our neutrino-nucleus that we use to fill with nitrogen. That's very nice. Neutrino written on them, so neutrinos to bring our factor. Yeah. Now, this shows you how we collected the data. We have 2 data taking modes. One of them is just the internal triggered data taking, which is what you normally do if you run a germanium spectrometer. And we need this data for calibration because if you take data in this way, you get like a statistic background line that is in there or around, while our physics data is externally triggered by the beam. And this means that we have photons in target and know when they arrive, so then read out our detector, and that's in microseconds. And this data is blinded. However, we take additional data in between. This off-beam data is background. And conveniently, this means that for each signal waveform, we also get a background waveform. We have the same statistic for both of them, which is also nice for the analysis. Zooming in here, in the end, we only use this 40 microsecond window for our analysis. And this is because we need for germanium to get this good energy resolution. You need the baseline before because you want to determine the height of rise. which means it helps if you know this level before very well, and we did the optimization, and turns out that using all of this as a baseline before gives the best results. The data analysis that I'm showing you here was for the data we collected last year, and our physics one was in total almost 8 weeks long. Now, what do we do when we get our data? The first step is to remove any pulses that are usable for the analysis. A good pulse is what you can see up here. So that is what we want to have. And then there are a lot of signals that don't look like that. First of all, we have this TRP reset. That's a practical feature on the way our data is read out, because we have this rise, this our signals, which means that the baseline increases more and more, but that cannot go on forever, which means at some point our P amplifier needs to do this reset and go back to the baseline level. It's not useful for analysis. Then we have a lot of spiky noise, and we also have this wonky shakes here. Some of this we can assign to the Allen films, which means we just cut out the periods when we fill this liquid nitrogen, and also shortly after, because everything settles, there's foil of the microphony. And then we have various cuts to get rid of all of these events. There is a last type of event that we did not remove from our first analysis, and this is this so-called slow pulses. Those are physics pulses that are created in the surface layer of the germanium diode. So we need the surface layer because it's a diode. And charges that are created in here, they need even longer to drift to the readout, and also part of the charges get lost, which is why they are called slow pulses. And because charges get lost, they are not reconstructed at the correct energy. Which means in the end it's justified to remove them from the analysis, and we are planning to do this for future analysis. But for this very first one, just to not have to deal with too many systematics, we decided to put them in, which is not a problem because you just need a backward model that takes them into account. Now we have our good pulses, like that one here, and we want to know the energy. This is done with a trapezoidal filter, where we extract the height of this step. And here in this figure, we have this examination to understand how well this works. And it turns out that we put a toy pulse on there, on our noise, then we get our signal out within accuracy, very accurately out within the energy resolution down to 200 electron volts. So this is really not a limiting factor. On the other hand, when we do the same here for the time when the charges arrive, so the middle of this rise is 50. In this case, we want to know the exact point in time. That is more challenging. That's the same comparison here. And now in this case, you can see this distribution gets asymmetric wider towards lower energies. And this is why we decided to set our energy threshold at 1.5 keV, because below, then depending on the detector and the noise, efficiency starts to play a role. So we decided to set the threshold at a place where the efficiency is almost negligible. So we have the energy spectrum and we have the time spectrum. That's the energy spectrum that we get out of it. Spectrum also shows how the cuts remove different lengths. So these are the typical TRP resets from the pre-amplifier. Then we have noise at low energies, and this overall reduction comes from the real rate, which has an efficiency of about 85%. And that is what we then are left with in the end. We can understand a bit better what's remaining there. What you can see, so what you see here is a bit clear that there are some lines left. Those lines are created in cosmic activation. That helps us mostly already during detector production, transportation on the Earth surface. There is still a bit of a contribution from activation of remaining neutrons inside the shield. But overall, these lines are not bothering us, but they are a bit helpful even because they can be used for the energy calibration to know, to be able to know what energy range we have in the end. Else, regarding the shield, so we have this passive shield, which in the end we estimated as a reduction of 10 to the power of 2, 10 to the power of 3, and then the active veto, so 10 to the power of 1 or 5%. And this results in about 350 counts per day in this region of 1 to 20 kV. Now, to further reduce this, we introduced the beam correlation, and this then turns out that so for the beam correlation, you still have to think on which window you are using for your analysis, and we examine 2 windows. That is because on the one hand, you can of course optimize with equal to background ratio. That is the case for this 10 microsecond window where you get stronger compression. However, for the final analysis, that's vacuum analysis, it's nice to have a wider range of background to be able to fix the background a bit more. So that is why we have a 40 microsecond window there, which we do with compression factor. But overall, I can still see that then end up with background rates that are comparable to 1,000 meter rock over, which is pretty nice of this. And also it turns out comparing the background, the internally triggered background that has lines here, with the externally triggered background is the beam correlation with the shaped wedges. And this for us gave us a chance to use this internally triggered background as our background problem. So we did not do Monte Carlo simulations to describe our background, but we just used this internally triggered background as our PDF for our likelihood analysis. The last thing that we worry about is potential beam-related background, because of course we cannot suppress this with the beam correlation. And what is potentially there are beam-related neutrons. However, it turns out that we expect over the whole run less than 1 count, which makes this background negligible, shown this with MNCP simulations. And the other thing that can potentially happen is neutrino-induced neutrons from neutrinos that act at shields and principally able to create neutrons. However, from this previous CSI result, we extrapolated that this is much less even than beam-related neutrons, so less than 0.01 counts. Also because this germanium setup has much more polyethylene than for instance iodide result, which means that we don't have to worry about the background. It's less than 2% of our cells. So to summarize, now this is the data that we collected over our beam camp. It turns out that not all detectors were stable enough for analysis, but we ended up with total active mass of 11.0 kilograms and total exposure of 10.2 gigawatt hours kilogram. Then that's the input from the data for our likelihood analysis. Then we need the PDF. So that's the signal PDF, which is short in the first part of my talk. So that here's the energy up to 20 kV, and here you can see neutrinos that arrive to 12 microseconds with continuous here microseconds. And then on the right side, the PDF in the background that, as I said, comes from this internally triggered data, and the background is flat in time and increasing towards lower energies. We combined all of this in an unbinned likelihood fit, and that is what we get out of it. What you see here is the energy spectra in the upper part and the time spectra in the lower part. In all these cases, the background has been suspected. And on the left is the off-beam data. on the right is the on-beam data. So here, and then here on the right, you can see the signal that is created in the 7 interactions. It becomes evident that the signal is clearer in time. That is also because with the time we have the time period before the neutrinos arrive, from the neutrinos and afterwards. But of course, it's not possible for energy because the energy is just the rise towards lower energies. And that's the numbers that we get here. So we have in the end the 7 signal of 21 counts and reject the null hypothesis of no 7 detection by 3.9 sigma. It turns out that we are a bit lower than from the expected from the standard model. That's 35 counts, but that is still within expected statistical uncertainties. We did a lot of tests, of course, but our best assumptions right now that this is mostly caused by statistics. So we just need more data to fully get behind this. It's of course interesting to understand what uncertainties and the speak about here up to 30% other statistical uncertainties. It's definitely by dominating in the future. The uncertainty of flux is 10% will be more important. And then we have a few other uncertainties. Small. The largest active mass already comparison. All of the results are summarized in this publication. If you want to know about all the details, and I, in the last part of my talk, want to give a bit of an idea of what will happen in the future for Gemini and for Coherent. This is first of all an overview of all the Coherent results, and you can already get an idea comparing the exposure here, germanium. With the smallest exposure, we already get 3.9 sigma from 3 weeks of running, which means that we collect much more data. It would be a great precision test of the standard model. That's a prediction how things could go. So this is the evolution over time for the spallation neutron cells. There are tables on what they expect for the future beam power will be. And this is convolved in this figure here. And what is on the y-axis here is the 7th cross-section. And what we studied here is for the different systematics, how things will evolve. So if this all the uncertainties stay like that, then in the next year there's the improvement, of course, to the statistics, but at some point the slides get flat. So it's interesting to do something about the other systematics. The next dominating one, the systematic is 10% from the beam. And this applies actually to all Coherent detectors because it was the same neutrino beam, and that is why Coherent set up this experimental effort called D2O. The goal of the D2O detector is to significantly reduce this uncertainty to within 5 S years, and they are doing that by setting up the strength of a water detector, where they are measuring the charge current due to scattering of the neutrinos from the beam. And this is because this cross-section has a very, very low theoretical uncertainty, which means a precise detection will make it possible to know exactly or much better this neutrino flux. And for Gemini, the other things that we need to work on is the energy scale, and there's things that can be done about the background. I mentioned the slow pulses already. We can cut away, and all of this will use the systematics. Yeah, everything goes very well. We end up with ±2% uncertainty. Now this figure is for an energy threshold of 1.5 keV, which is another goal to lower this threshold, which means even if not everything goes as well as planned, and in particular not collect all of this data, it means that we can get to high precision because the 7th expectation increases towards lower energies if we are able to successfully lower the energy threshold. And what we are trying to do here is to apply machine learning. That is, I cannot unfortunately say too much about that, but a few details at least here. So what I'm trying to do there is time series clustering. That's unsupervised learning, which means that I don't have to put in any information on what I expect there actually. And it turns out that already works very well. For this example, 4 clusters were found. Here you can see the average pulses from this cluster, the cluster centers. The green one is the normal germanium pulse, the actual signals. Then the algorithm is very well capable to identify the resets here, and also to detect 2 other classes of noise. There are spiky noise, very like there's this very characteristic down and upwards jump, and then there's also this more fuzzy type of noise. And the strategy now is, first of all, to use this tool of machine learning to better understand what kind of noise we have there, and to see if we can get rid of our experiment. For example, this noise has a very particular frequency of 90 Hz, so we hope that for the future data taking, we can just avoid the source and not have these events at all. And the next step then, once this has been successfully carried out, is to also apply this algorithm to the data that we have already collected to lower the energy threshold and future data. So that gives a bit of an idea how this could look like. What you can see here is the distance of events to the cluster center. The green ones are the signal events. They are all pretty similar, which means that it's possible to identify them. And then we have the different types of noise, the blue and the orange one here, which are the resets, and this characteristic spiky noise, also close, and then other noise is a bit more fluctuating. But overall, the positive thing here is that all signal events are very close together. And plotting then on the left here, the blue, what remains after only having the signal cluster, already does the job of data cleaning very well. So these are all the result events that are successfully removed. And down here, this noise peak is also, in this case, completely removed. It turns out that actually this double shape that you can get an idea here comes from this higher spike here, comes actually from the spiky noise. It was interesting to see that. And then on the long run, the idea is to finally use this algorithm for triggering, to implement it on HPGe and to be able to fully run the experiment itself triggering, which is interesting because this means we get even more background events, not only one waveform between the beam, but much more between the beam triggers, but much more. And the other thing that is interesting is that there might be interesting physics hidden in very delayed correlations to the beam, which we don't know about and which we cannot do with the current way that we take data, but we are able to use this trigger routine, then might be able to get these events. And right now, it's not possible to run everything in self-trigger mode because of this noise events, because our trigger algorithm triggers on this noise, and that totally overwhelms our data acquisition. You get an idea here because there's this tiny gap. But the hope is that this can be avoided with the machine learning if we are able to not trigger on all of these messages. So that's the future of Gemini. Yeah, very briefly, the future of Coherent, what is for the future, but what else is going on. There is much more than CEvNS that you can do at the spallation tensors, and there are charge current interactions at higher energies. There are 2 results out. One has been achieved with the neutrino cubes. Here, the goal was to measure this neutrino-induced neutron background. And here it turned out that this one is actually much lower than predicted by theory. The same was true for the charge current interactions on sodium iodide, which was also some data that was collected with setup code naive. And in this case, it turns out that from the prediction, which was done with a code called Mali, that in comparison, only about 41% of the events were actually measured, which makes it very interesting for the people who do this theory calculations to investigate why there's this such discrepancy between experiment and theory. This data has been collected with sodium iodide crystals. Coherent has a lot of them. Currently we are building a setup called naivete, which will end up to be 3.4 tons of sodium iodide crystals. And this goal here, first of all, is to measure 7 sodium iodide. Some of these modules are already deployed in neutrino alley, so there's already possible background data. The next setup will be up and running. More statistics is also collected with Argon up to recently. So the data set has been extended by a factor of 3. Its analysis is also currently ongoing. And for the bit farther future, the setup will be significantly increased. So there's requires that this has been meanwhile delivered to Oak Ridge. And in the end, that will be 750 kilograms of liquid argon. Will also be deployed in neutrino alley next year. And finally, we have another effort to lower the energy threshold. Right now, germanium is the detector with the lowest energy threshold, but it looks like that CSI detectors, these dip crystals, it's possible to also lower this energy threshold down to 4 kilo-electron volts. And how to do this is to cool down the detector for each mean, which increases the light field by a lot and leads to this very low energy threshold. Currently, this effect is under study, and there's a setup that is currently under commissioning. Also for the SNS, there's a lot going on. There's an upgrade, beam power upgrade that unfortunately meant that after the side testing, we could not collect any new data. Beam. However, it will mean that in the end we get a beam power of 2.0 megawatts, which is more neutrinos, which is great. And then also in a bit farther future, in the 30s, the second target station is being built. So also from that side, there will be more neutrinos. So to sum it up, yeah, I showed you that I explained to you what Coherent nuclear scattering is and why it's interesting to infect it, and how to successfully do this at neutrons with Oak Ridge. Up to now, that happened 3 times. First, this is iodide crystals and argon afterwards, flight. Now we have this first effect in ionization energy with Gemini, where we had a significance of 2.9 sigma. This is first data set. And the goal is now to collect much more data to significantly reduce the statistical uncertainty and have a precision test of the sample of particle physics. So thank you for your attention.
Thank you very much. We need to be kicked out of here in 5 minutes, so we have time maybe for one full question.
There's a question online. Billy, do you want to, we can hear you if you just want to speak, or we prefer.
Oh, sure. I'm happy to speak. Thanks. That was a really super interesting talk. I actually have a bunch of questions. I was wondering, could you just explain the D2O detector on page 31 a bit more, please?
Okay. Yeah. So there is this heavy water inside pipe stuff, and that signals that are created here are that are there. And of course, this thing also has a shield and neutron. And
did you say it was in a cryostat?
It's cylinder. Okay, cryostat is probably longer. So.
Okay, thanks.
There's also a publication if you want to have a detailed explanation.
How large is it?
It's more or less 2 meters.
I think we should better get going, Ryan, really quickly, or?
Long stuff.